We've learned before that the mass, the atomic mass unit that's listed on the periodic table, is also the value for the molar mass, or the mass in grams of 1 mole of a particular substance. The units for this are grams per mole, and if you want to find the molar mass for a compound, you're going to add up the individual molar masses of that compound to get the total. Now what we'll do is we'll always use 2 decimal places for our molar masses when we take them off the periodic table. This will allow us to be consistent with each other no matter which periodic table we're using. And it will also allow us to make sure that the number of significant digits is not limited by the molar mass. What we're going to do now is derive a formula that relates the number of moles that we have of a particular substance and the mass of that substance in grams. So when we look at a sample, if you have the number of moles of neon, for example, we've got 1 mole of neon. So if you've got 1 mole of the substance, we simply read the number off the periodic table to find its molar mass, which is 20.18. And in order to find the mass of 1 mole of the substance, it's going to be the same because 1 mole has a mass of 20.18 if we have 1 mole of neon. Now for the molar mass of CO2, we had to add up the values for carbon, which is 12.01, and for oxygen, which is 16, times 2, because there are 2 oxygens. So we have 32 plus 12.01. That gives us a total of 44.01 grams per mole. If we have 1 mole of carbon dioxide, then the mass of that sample will simply be the molar mass, which is 44.01 grams. For sodium chloride, the molar mass is found the same way by taking the total of the molar mass of sodium and chlorine, which gives us a total of 58.44. So if we have 1 mole of sodium chloride, then the mass of sodium chloride that we want is 58.44. And so what these values mean is that this is the mass in grams that will give me 1 mole, or 6.022 times 10 to the 23 of that sample. So in 20.18 grams of neon, we have 6.022 times 10 to the 23 atoms of neon. If we have 44.01 grams of carbon dioxide, we have 6.022 times 10 to the 23 molecules of CO2. And for sodium chloride, if we have a sample that's 58.44 grams, then we have 6.022 times 10 to the 23 formula units in that sample. Much like before, we're not always going to be dealing with 1 mole, so we need to be able to manage different quantities of the substances. So if we only have half a mole of neon, then in grams, we need half of 20.18. So to find the mass, we'll take the number of moles that we have, which is 0.5, and we'll multiply by the molar mass, which is 20.18. And later on, we'll do the math, but for now, it's just the concept. Much the same way, if we have 2 moles of CO2, we're going to need twice as much as this because this is the amount of only 1 mole of CO2. So if we want 2 moles of CO2 and we want to know how many grams that is, we need to multiply the molar mass by the number of moles. And lastly, if we have 1/4 of a mole or 0.25 of a mole of sodium chloride, then we're going to need 0.25 times 58.44 grams per mole. And if you want to think about this algebraically, what we've done here is we've taken the grams per mole and we're multiplying by the number of moles we have. And so when we look at the units here, algebraically, when we multiply these 2 things, we're left with the grams. So what this has done is it has given us a formula, which is that the mass of a sample is equal to the moles that we have in that sample times the molar mass. So the symbol that we use for mass is M, much like we would in other courses. The small n is our moles, which we've used in previous lessons. And a new symbol is mm, which I use for molar mass. Now, this is one way to look at the formula, but the most common way to look at this formula is in terms of moles. So the moles that we have in a sample is equal to the mass in grams divided by the molar mass. So this is our formula. This is the moles. This is the mass. And it's very important, this has to be in grams. And this is our molar mass, which is in grams per mole. And much like we did with our last formula, we can develop our triangle. So our mass goes on top is equal to the moles that we have times the molar mass. And this will give us the important rearrangements of the formula. Let's do some examples. So the first question here is asking us just to find the molar mass of water. So just to make sure that everybody is clear on that, the formula for water is H2O. So what we need to do is take the sum of the individual molar masses of the atoms in the formula. So we have 2 hydrogens and we have 1 oxygen. The molar mass of hydrogen is 1.01, so we need to multiply that by 2. The molar mass of oxygen is 16.00. And when we add these up, we get a molar mass of 18.02. It's important to remember that the units for molar mass are grams per mole, because it's the number of grams of 1 mole of that sample. So in our next question, we're asked to find the mass when we're given a particular amount of moles of water. So we'll put our triangle here to remind us, if you want the mass, we cover that up and we find that it's equal to the number of moles that we have times the molar mass. So mass is equal to the number of moles, which is 2.2, times the molar mass, which is 18.02 grams per mole. And the value that we get is 39.6, but we need to report this to 2 significant digits. So this rounds to exactly 40, so we can either write it as 40 with a decimal point to show that both of those are counted or significant digits, or we can write the number in scientific notation as the number 4.0 times 10 to the 1. Either of these is acceptable and shows that we have 2 significant digits. The next question asks us to calculate the mass of 0.234 moles of copper. So again, we need to take the mass and we need to, the moles, 0.234, and we need to multiply by the molar mass of the substance that we're dealing with, which is copper. And copper is an element, so we simply take the molar mass of 63.55. And we are left with 14.9 grams, which is recorded to the correct number of significant digits. And you'll notice in both of these cases, the molar mass has a significant digit number, but it's not limiting the answer. And you never want a constant that you're using, which is what the molar mass is, to limit the number of significant digits. So you should go ahead and pause the video and try this example. Calculate the mass of 2.5 moles of sodium sulfate. You'll need to first calculate the molar mass of sodium sulfate. And you should find that the mass is 355 grams. Okay, if you had trouble, what you always want to do whenever you have an incorrect answer is first double check that you've got the correct molar mass. And in this case, the molar mass is 142 0.05. You need to take 2 sodiums, 1 sulfur, and 4 oxygens and add them up. Let's try some examples where we take the mass and convert it to moles. So if we look back at our triangle, the mass, the moles, and the molar mass. In this case, we want to know how many moles we have, which is our N, in a particular mass of sample, which is our M. So to solve for moles, you need to cover up the moles, and you find that the formula is mass divided. So moles is mass divided by molar mass. We're dealing with copper, so the molar mass of copper is 63.55. And we have a value of 0.0157. And we're finding the moles, so the units are MOL. In this last example, we have 1 gram of water. So in 1 gram of water, to find out how many moles that is, we need to take our mass and divide by our molar mass, which we've previously calculated at 18.02. And what we find is that you have 0.0555 moles of water. This example was chosen intentionally because even though we have a 1 gram sample of water and of copper, we have a different number of particles in that sample. And that's because the mass of 1 mole of a given sample is going to be different because the atoms themselves have individual masses. And that concludes our lesson relating the mass and the moles of a particular sample.